The overall goal of my research is to use mathematical tools, particularly from controls and robotics, in order to understand how people walk and then develop better interventions for these people.
It's all about studying how people move, how people walk. If we can understand that, then maybe we can identify some key features that we can translate from healthy subjects to maybe those who need assistance walking. This exoskeleton allows us to assist the user as they're moving and may be able to help those who just can't walk themselves or maybe just need help doing physically intense labor.
Okay, go ahead and stand up.
My research, and really most of the research going on right now, is more base level, understanding how do people interact with exoskeletons. And we need to know this before we can really implement it wide scale.
Here we have our ankle exoskeleton. How it's controlled is through a pneumatic air compressor that feeds into these two chambers. The pressure difference between the two changes the position of a piston. This, in turn, changes the angle of the ankle exoskeleton. Additionally, we have a force sensor in the heel and in the toe. The pressure difference between these changes how the exoskeleton moves. As the user is standing and as they roll off to the ball of their foot, the exoskeleton will move and push off, providing assistance to the user.
So right now we're testing with able-bodied subjects, in part because they can handle the really long experimental trials. In order to measure how people move, we use what's called a motion capture system, which has a whole bunch of infrared cameras all around the room, and that can track the markers on the person. There are 16 reflective markers we have to put on their legs, and then 4 to 6 EMG sensors. These are sensors that measure how much people are using their muscles.
We then have a program that rebuilds a skeleton of the individual based on the position of those markers.
Ready, go.
We're then able to see the person walking and moving in real time. We have a treadmill centered in the floor that is split belt. We can record different forces of the person walking on the treadmill. So as they walk, we're able to record the force from one foot, and then we can see that force transfer go to the other foot for each step.
We do a bunch of 3-minute trials. So we have the people walk with one set of exoskeleton control parameters. And we record, how are their legs moving, how much muscles activation are they using, how much energy are they expending.
As we record these, we can see the angles that people move through their joints, how their knee is bending, their ankle is bending. We're then able to chunk these out into steps and then analyze those steps to see if there's any patterns that we can pull out of that.
So at the end of each trial, basically we have a survey and we ask people, how comfortable did you find the exoskeleton? So this is much more of a subjective measure. Then we can analyze, see, is there any relationship with how they're moving?
Once we record all this data with a healthy subject, we're able to analyze it and potentially pick out key features that are desirable to have as they walk. Then we can study how people who have problems walking, whether that be due to a stroke or other ailment, then we can see the differences. We can look to see where the mismatch lies. Then we're able to potentially fix that and correct that with the exoskeleton.
I am optimistic that eventually we're going to get some commercially viable exoskeletons. And I think we will be able to get some of the other things like the controllers and the comfort and such worked out. I don't think it's going to be super quick or super soon, but I think we will get there.